Hi, everyone. Welcome. Thank you for joining us today. We're going to be talking about a paper that was just released last week called In the Shadow of Wind Energy, Predicting Community Exposure Annoyance to Wind Turbine Shadow Flicker in the United States. You might notice that you have joined in muted only mode. We have over 50 attendees, and so this is just for management purposes. We do want to hear from you though. So at the bottom of your screen, you can usually hover over the bottom of the screen and get ability to select Q&A. If you will, answer questions there in Q&A, and then we will answer them at the end of the presentation. If you have technical issues, you could put it in chat. We do have somebody monitoring technical issues. Hopefully there are none, and then feel free to ask those questions at any time during the webinar, and we'll get to them at the end. So why don't we step into this? Just need to offer this disclaimer. Although this work was funded by the U.S. Department of Energy's Wind Energy Technologies Office, they are asking us to say that this work is ours and only ours, and the opinions expressed today are not necessarily theirs. And the same is true for the University of California and Lawrence Berkeley National Lab, our employer. So the project team is shown on the screen, and everyone is on the call as well. I'm Ben Hohen. I'm a research scientist at Berkeley Lab. We're joined today by my colleague, Joe Rand. Also on the line are Ryan Hawk and Ken Kaliski from RSG, and Ryan Darlow from Vera Renewables. I will point out this isn't a particularly diverse team. I didn't notice that when I first put these photos up, but I am glad to report that these are some of the most qualified individuals that I had the pleasure of working with on this project. And I look forward to being able to allow you to hear their voices. Ryan Hawk and Ken will talk after me, and then Ryan Darlow and Joe will be on the line to answer questions as need be. So this is the goal of the presentation today, to cover a little bit of background on the subject, talk about the data that we used for our analysis, cover the methodology used for the analysis, and then dive into results and ultimately discussion of those results. At that point, we'll have an opportunity to answer questions. There we go. So this is a video. Hopefully you all will be able to see and hear. Let me start this up. So this is an example of shadow flicker. In this home, you can see the light is dimming and brightening at a relatively slow rate. This is what it's like to experience the sun shining through the blades of a wind turbine. And as you can imagine, this would be pretty annoying. The individuals that are experiencing this are indeed have the light shining through the blades of the turbines. And this is an occurrence that does happen at some points during the day for some locations. Shadow flicker is this effect of pulsating light and shadow. And it's most common in the morning and evening hours to the west and the east of the turbine when the sun is at a very low angle. This is not unlike the flickering that you might experience when the sun is at a low angle and it's shining through trees that you're driving by, and they're flickering through your side window. Though, as you can see, the wind turbine flickers at a much lower rate than would be the blinking of trees. One quick note about the link between shadow flicker and health impacts, and we do review this in a little bit more detail in the paper. There hasn't been a strong link to health impacts, though there have been plenty of claims of annoyance, and annoyance is more of an attitudinal reaction to the wind turbines than actually a health impact. And that's what we're going to be talking about today, annoyance. So how is shadow flicker generated? As I mentioned, it occurs when the sun is at a low angle. along the horizon. That is called its altitude. As well, it has to have an azimuth that aligns the turbine and the house for it to be experienced on the house. So everything, the sun, the turbine, and the house have to be in that same azimuth angle. As well, there can't be any intervening structures or vegetation. In these figures, you can see some trees here next to the house. Those could block shadow flicker for those periods where it might occur at this house. And then, of course, you need to have the sun shining brightly. You can't have cloud cover and still have shadow flicker. So on the left is a situation where this house is not experiencing shadow flicker. And on the right, everything aligns so that this house is experiencing shadow flicker. That is exactly what we would be talking about in this presentation. So those characteristics that I just defined can be put into a model, and that model can then predict the hours of shadow flicker that might occur in various locations around a single wind turbine or multiple wind turbines, as shown here on this, these two figures. Let me first just note that the word model will be used on multiple occasions throughout this presentation. We will be talking about this shadow flicker model, which predicts the numbers of hours that shadow flicker would be received at locations. And later we'll be talking about regression models. Each one of these models does an attempt at trying to imitate or predict the reality, and they're very useful to better understand some of these complicated relationships. So going back to the shadow flicker model, you can see that quite close to the turbines, the numbers of hours that are expected to be received in a full year are quite high. And as you move further and further away, they're lower. That's because the sun is only rarely at the angle to allow that shadow to extend that far away. As well, you can see that the extent of the shadow flicker stops out here on the edges, like a bow tie or a butterfly. That is the limit at which practitioners assume that the shadow itself is so diffuse that it isn't it is barely noticeable. So we too model this out to a certain distance. That shadow flicker hour is expressed in hours per year, total hours per year, or minutes per day. Now, there's sort of two common ways to model shadow flicker. There's the worst case and the real case. The worst case basically assumes the turbines are always operating, there is never any cloud, and there's never any cloud cover. This is effectively, just as it sounds, the worst case scenario. But in fact, for most homes, it is not, doesn't approximate what they would actually receive. To do so, we estimate what is called the real case. And in that case, we are adjusting for the frequency of cloud cover that might be experienced in a certain area, the periods of time where the turbine would not be operational, which of course the wind doesn't blow every day, all the times of the day. And then we also take into account wind speed and wind direction, because that matters in terms of the way the blades are shaped and therefore the amount of shadow flicker. Some practitioners take into account land cover. We actually looked at this in our model and didn't find it made a difference. So we aren't using it in our full model as we estimate for the purposes of the remainder of this presentation. We are going to be using this real case metric throughout the presentation. So when you hear us talk about shadow flicker, we're talking about shadow flicker estimated real case and hours per year. Finally, you should note that the relationship between worst case and real case is roughly 3 to 1, 30 hours to 8 hours, not exactly 3 to 1, but that 3 to 1 ratio is something we'll talk about again. So what is annoyance? That was another focus of this work. Annoyance is defined by at least Linval as a feeling of displeasure associated with any agent or condition believed to affect adversely an individual or a group. So it often doesn't result in negative health consequences, but it surely can be bothering to some people. We all know the dripping faucet kind of classic annoyance where you just got to get up and figure out how to stop it. So it clearly can bother you, no doubt about it. We're going to be talking about annoyance that we measured in a survey, and we measured it using a 5-point scale from not at all annoyed through slightly, somewhat, moderately to very annoyed. And I'll talk a little bit more about that as we get into that survey. So we aren't the first people to look at shadow flicker. The first study that we found was all the way back in 1984 that noticed how shadow flicker could cause epilepsy and nausea and seizures to individuals when that flicker was at a very high RPM, 60 RPMs. This is not unlike a strobe light, which can be really annoying if having to experience for a long time. Modern turbines operate at around 17 RPM, so it's much slower. So these kinds of things don't occur for wind turbines. You saw that in the video. Johannes Pohl in Germany took a much more closer look at the effects of turbines in 1999 and found that there were various scenarios where the flickering could be annoying depending on how often those rooms in the house were exposed to shadow flicker and where those rooms were located in terms of the side of the house. So that was work we're building off of. As well, Health Canada looked at this issue more recently in 2016, finding that there was an apparent relationship between shadow flicker exposure, that modeled shadow flicker, and annoyance, although it was very weak when additional characteristics were included in the model. And finally, I will note, and we'll get back to this again later, we have already looked at the same issue, which is how well can we model something that people might experience in the real world, and how does that relate to their reactions as collected by the survey data for sound of wind turbines. So wind turbine noise perception and annoyance is something we looked at a paper that we released in 2019. And we're going to touch on that paper briefly at the end of this presentation. So that sort of sets up what we thought were the important aspects that we should look at as it relates to the US population. We wanted to look at the relationship that individuals have to turbines, how much they could perceive shadow flicker, and if they were annoyed by that shadow flicker. We started this work by collecting data around the country. In 2016, we conducted a national survey of wind turbine neighbors, ultimately asking 1,705 people about their reactions to the turbines that were in some cases just outside their window. A good portion of those locations, we were able to model that shadow flicker, and that's what we're going to be using today for our analysis. Ultimately, there were 747 respondents, around 61 wind turbines in 17 states. That comprises our shadow flicker model data set. If you want more information about this wind neighbor survey, you can simply Google wind neighbor survey, and there's plenty of information about the survey instrument, the data collection, and all the papers that came out of this work. So this is actually a copy of that survey instrument, just the portion that I want to focus on today. We asked people, do the blades of a wind turbine ever cast a shadow on your property but outside your home? And if they said yes, we asked them, do the blades of the wind turbines ever cast a shadow in your home? And so they could answer that, and you'll see those answers in the presentation as we go forward. And then we asked them, to what extent do you feel annoyed by each of the following aspects of that local wind project? And what we're focused on now is the answer to C, shadow flicker. As I mentioned, it's a 5-point Likert scale. Not at all, slightly, somewhat, moderately, and very are the answers that they could have given us. And we have grouped these into just 3 categories: not at all, collapsing the middle of slightly, somewhat, and moderately into one category, and then very annoyed as the final category. So 3 different categories for the responses. So those are the key data that we're looking to better understand whether we can predict using a model of shadow flicker. So I can't remember, Ryan. Is this where I hand it over to you, or do I keep on going?
It is, yeah. No, it's me. Yeah.
So let me introduce Ryan Hawk.
That's me. Hi, Ben. Thanks for that great introduction. So with all that, what did we actually do here? So we modeled shadow flicker at about 35,000 residences within 2 kilometers of a turbine in 61 discrete wind projects across the US, like Ben showed in the map previously. That totaled about 3,000 wind turbines that were modeled. And so of those 35,000 residences, 747 of them were survey respondents. And so next slide, please, Ben. Great. And so here's our first picture of the results that we came up with. So let's start with this the plot on the top here. So this is organizing all of those 35,000 residences by their distance to the nearest turbine, and then shading them based on if they had any modeled shadow flicker at their home or not. And so what's shown here in the orange is that, you know, the largest portion of the sample did not have any modeled shadow flicker. But once we start getting closer to the nearest turbine in the dark gray down at the bottom of that top plot, yep, that's where we start to see shadow flicker at residences. We also have this green line going across the plot, and that's the proportion of the sample in each 100-meter bin or group that has modeled shadow flicker. And as one may logically expect, as residents get closer to the turbine, there is a higher proportion of them with any modeled shadow flicker. So looking at now, just zooming in more on those with modeled shadow flicker, so the dark gray shading at the bottom of that top plot. Now we bring those down to the bottom plot here, and however, rather than organizing them by distance to the nearest turbine, this plot is organized by distance to the turbine contributing maximum shadow flicker. Now, this might not necessarily be the closest turbine to a specific residence. For example, if a turbine was located directly north of a residence, it would not have the opportunity to provide any shadow flicker there. So what we can see from this bottom plot is that the largest proportion of residences actually have shadow flicker below, or sorry, let me say that again. The largest proportion of residences with shadow flicker that have modeled shadow flicker have less than 8 hours per year. And this number is important, really based on an early German guideline. It's equivalent to the guidelines that came out of some of that original work that was mentioned before. And so we're then showing with this blue line going across the plot of what is the proportion of residences with modeled shadow flicker that have that receive more than 8 hours per year. And you know, once you're within 100 or 1 kilometer, 1,000 meters, you know, it really starts to shoot up. And by about half a kilometer or 500 meters, we're up to about 90% have of those with any modeled shadow flicker have shadow flicker above 8 hours per year. Next slide, please. Okay, so now let's hone in on the survey results. So first we're looking at perceived shadow flicker. So the responses on the survey saying that yes, we either perceive shadow flicker in our home or on our property or not at all. And so these plots at the bottom, they're grouping all of the respondents by their shadow flicker exposure, either 0 hours or no shadow flicker, 0 to 4 hours per year, 4 to 8 hours per year, 8 to 30 hours per year, or more than 30 hours per year. Those are the horizontal groups going across. And then we're looking at the proportion of those respondents that were able to either perceive shadow flicker in their home, on their property, or not at all. And so this first plot on the and I should also mention that the bar widths do represent the proportion of the sample represented in each exposure bin. So that first bin on the left of the, for 0 hours, that was the largest bin. There were the most respondents in that bin out of any other bin. But so what we can see from both of these plots is that really as the shadow flicker exposure increases, so does the proportion of respondents that perceive shadow flicker. The plot on the right is really the same as the one on the left, except we've removed those with no shadow flicker, with 0 hours of shadow flicker. And so it kind of zooms in more on this dose response relationship that we're seeing, where as there's increased exposure, there's also increased more people are noticing shadow flicker. The last things I'll note, looking particularly at the plot on the right, is that the proportion of respondents who reported seeing shadow flicker on their property remains relatively consistent among the different exposure bins at about 15%. And also above 30 hours per year, all of the respondents noted that they could see shadow flicker either in their home or on their property. Next slide, please. So now we're on to annoyance, and this is really showing the same information, but or the same format, but now rather than shading by perceived shadow flicker, now we're looking at shadow flicker annoyance. So the red being very annoyed, and the lightest color being no shadow flicker in they reported no shadow flicker in their home. And so looking at the plot on the left kind of suggests this similar dose response relationship as a larger proportion of respondents reporting annoyance. But once we remove those who did not report shadow flicker in their homes, that lightest color, we get the plot on the right, which shows that there are similar proportions across exposure category. And so what I mean by that is that a similar proportion of respondents in the 0 to 4 exposure bin were annoyed or not annoyed as those in the bin above 30 hours. So this is suggesting that there's not a direct dose response relationship between shadow flicker exposure and between shadow flicker exposure and annoyance. And so maybe there are other things going on, and that's what we'll flesh out here as we continue. So next slide, please. Right, and so how do we figure those things out? Well, we turn to regression models to predict these interactions and between variables. And so can you forward? So our team implemented an ordinal logistic regression model to predict both perceived shadow flicker and shadow flicker annoyance. Those are our two dependent variables in separate discrete models. And we use independent variables to see how they're uniquely correlated with these outcomes with the dependent variables. And so can you go to the next slide, Ben? And we'll look at the independent variables for these. So we grouped our independent variables into 3 different sets. The first set are the basic variables, things we absolutely need to be able to predict these outcomes. And so the basic variables include estimated or modeled shadow flicker in hours per year, also project participation or one's relationship with the project, that is, were they compensated for the project itself, or are they hosting a turbine on their property, and also the distance the home is from the nearest turbine. The second set are observable variables, things like project and wind turbine characteristics like hub height, rotor diameter, rotor tip speed, and the age of the project. We also included the number of turbines that respondents reported being able to view from their property, and also if they moved in before or after the project was constructed. The last set of variables are the subjective or attitudinal variables. And for that, we looked at average annoyance to typical community stressors, such as vehicular traffic, streetlights, agricultural machinery, and other mechanical devices. And the last variable is, does the respondent like the look of the project? So yeah, let's just go to the next slide. So how do we measure all this? So the first is, how do we look at the strength of these independent variables, each individual one? And so to do that, we use what's called the Akaike information criteria, which represents the impact of the model fit when that particular variable is removed from the model. You could think of it as maybe the big yellow taxi metric, where the model doesn't know what it's got till it's gone, I guess. But really what you need to know about that is that higher AIC values are what are going to signify stronger predictors. And in terms of the model itself, we used a leave one out, cross one validation to determine how strong, how effective our model was in making these predictions. And a leave one out, cross one validation routine essentially runs the model by leaving out each individual respondent and trying to predict that known response. And so with that, we can come up with a proportion predicted correctly or percent correct. And so with that, some results. Okay, so what we're showing here are the results of our regression models for both the perceived shadow flicker and shadow flicker annoyance. Perceived shadow flicker is shown in purple, and shadow flicker annoyance is in orange. The bars represent the change in AIC value, larger values being stronger predictors. And if they're bolded, that means they're statistically significant. And we've grouped the independent variables by the sets that I described earlier, basic, observable, and subjective. So for perceived shadow flicker, what we see is that shadow flicker, the distance one is from a turbine, the tip speed, and if they moved in after or not, were the strongest and significant variables in predicting if one would notice shadow flicker. What's notable about the perceived shadow flicker model is that none of the subjective or attitudinal variables were significant. However, or conversely, for the shadow flicker annoyance model, the subjective variables were the most important predictors of shadow flicker annoyance. And when all of the variables are included as shown here, modeled shadow flicker itself was not actually significant. And in terms of the explanatory power of the model, perceived shadow flicker responses were predicted correctly 70% of the time, and shadow flicker annoyance was predicted correctly 65% of the time. And with that, I'd like to turn it over to my colleague Ken Kaliski to talk about noise and shadow flicker together.
Thanks, Ryan. So as Ben mentioned, in 2019, we published a paper on predicting audibility and annoyance to wind turbine noise. And so we thought this would be a great opportunity to compare the factors that contributed to noise annoyance and noise audibility to shadow flicker annoyance and perception. So we move to the next slide. So on the left is the same chart that Ryan just showed, showing the importance of the different variables in predicting one's whether they can perceive shadow flicker in their home and whether they're annoyed by it. Again, the perception is in the purple bars and the annoyance is in the orange bars. And on the right side is what we found back in 2019 in our paper in the Acoustical Society of America, where we show audibility in purple and annoyance in orange. And what you can see is that generally the pattern is the same. That is, the perception of the shadow flicker or noise is mostly due to the direct variable of exposure. So on the left side for shadow flicker, it's the number of shadow flicker hours exposed or modeled at that home. On the right side for wind turbine noise, it's the maximum 1 hour equivalent continuous sound level at the home. On the other hand, for annoyance, we see again the opposite effect, where subjective variables are the most important in predicting one's response to wind turbine either shadow flicker or noise. And in fact, like the look of the project in the bottom variable was the most important variable in explaining annoyance for both shadow flicker and noise. But other subjective variables are also important, as Ryan mentioned, the general annoyance, and for noise, prior support or opposition, and noise sensitivity. So we see that they're very much related in terms of how people react to those exposures. Next slide. So how does this information inform the regulation of shadow flicker? So on the next slide, we can see that we essentially took a look at all of the states and counties in which we evaluated and modeled shadow flicker and noise. And we found that most of the counties don't enforce any limit on shadow flicker. In fact, of the 70 counties that we reviewed, only 13 had shadow flicker ordinances, and of the 17 states, only 2 had shadow flicker limits. And of those, the 30-hour per year limit was by far the most common limit. And as Ben mentioned, there's both real case and worst case. You could look at it both ways in terms of modeling. And unfortunately, only 2 of those actually mentioned worst case or real case. It is pretty undefined or ambiguous in almost all of the cases. We've found in the author's experiences in the US that real case is used where the standard is ambiguous. And that kind of makes sense because real case is essentially what you'll be measuring out there if you actually went out and measured shadow flicker. But again, there's significant room for interpretation in these ordinances. And the question is, in the absence of regulation or ambiguous regulations, is there anything that can be done about that, or is this a big problem? And so we looked at that in terms of how shadow flicker relates to noise regulations. And what we can see, I guess the question is, do sound regulations offer a proxy for shadow flicker limits? And to demonstrate this, we essentially modeled both sound and shadow flicker on the same graph. And this is for a project within, or one of the projects we analyzed. And you can see the sound levels that are modeled are shown in the isocontour lines, and the shadow flicker levels are shown as the different shades of color, the green, the orange and the blue color. So let's take an example, for example, the 45 decibel contour line, which is shown in orange. And you can see that 45 decibel contour line contains all of the orange shadow flicker, and that orange represents represents 30 or greater than 30 hours per year of shadow flicker. So this means that were there, in this case, a 45 decibel sound limit, it would also mean that all of the homes would be less than 30 hours per year of shadow flicker. Similarly, if you look at the entire study area across the US, we found that over 90% of the homes are protected with a 45 decibel limit. Over 90% of the homes are protected even with an 8-hour per year exposure to shadow flicker. So I guess the answer is yes, sound limits can serve as proxies for shadow flicker limits. The opposite isn't true, however. Shadow flicker limits can serve as protective of noise exposure. And that's because you can get really close to a wind turbine and have 0 shadow flicker if you're to the north or to the south of the wind turbine because of the way the sun sets and rises to the east and the west. Right. So with that, I'll go to our summary and conclusions. So the impetus for this project is really that shadow flicker can be annoying to some people around wind projects, and it can also be a design constraint for developers where there are regulations. And so we looked at homes near wind projects and developed models to predict residents' perception and annoyance to shadow flicker. And we found that a relatively small portion of the population near wind turbines experience any shadow flicker, and most of those that do are relatively close to the wind turbines. And using our prediction models, we found that people's perception of shadow flicker, that is, whether or not they can see the shadow flicker in their home, was most strongly correlated with the number of hours per year of shadow flicker that are modeled to be at their home, or shadow flicker exposure. However, the annoyance to shadow flicker was most strongly correlated with subjective variables, that is, with perceptions of the wind project aesthetics and general annoyances people have to other things, non-turbine factors. And then with respect to regulation, we found that the ordinances that exist rarely mention shadow flicker. And if they do, they rarely define whether the pre-construction analysis needs to have modeled real or worst case limits. But even so, we found that sound level limits, reasonable sound level limits, could serve as proxies for shadow flicker limits in their absence. And with that, I just want to mention on the next slide that this paper is the paper which was published in Energy Research and Social Science is available for free downloading at the LBNL publications website. The link is shown here. And now I'll turn it over to Joe Rand to manage questions that you may have.
Yeah, and just quickly there, we'll put the link in for the paper into the chat so that you guys can just click on it right from this webinar. As well, when you got the invitation to attend today, that link directly to the paper would have been in there. So 2 ways to get at it. Eventually, you hopefully should be able to Google something along the lines of shadow flicker wind turbines or Berkeley Lab shadow flicker and find the paper. Often I find it takes about a week for Google to catch up, but that should be possible also.
Yeah, so we have a pretty healthy Q&A conversation going on, and I invite everyone to submit additional questions. We've got plenty of time for a question and answer now and discussion. I think I'll start. We answered a few questions by typing in answers as presenters were talking. So I'll start by just walking through a couple of those, and there may be some discussion there, but then I'll move to the open questions after that. So the first comment we received was an encouragement to use health impacts more clearly. So the questioner says there may be no link to physical health impact due to shadow flicker, but don't be dismissive of mental health impact. This can be just as important. Long-term continued annoyance can have significant mental health impact and should be addressed. This is something we thought about in the paper, and if you do go and read the actual paper, you'll note that we mentioned that future research should perhaps focus on the combination of annoyance and stress symptoms, which might be more directly linked to health outcomes, rather than just using a metric of self-reported annoyance, which is what we focused on in this paper. So hopefully that could be done in future work, and we agree there. Someone asked whether the slides would be available after this webinar, and just to be clear, absolutely, we'll send those out to attendees and make this slide deck as well as a recording of this presentation available on the Berkeley Lab Electricity Markets and Policy website. A couple others that were already answered. Yes, thanks for navigating to this slide. The bottom graph here is shown in real case hours rather than worst case. So thanks, Ryan, for answering that. And then there was some confusion. Actually, I left this question open to begin with, but there was a little bit of confusion about the finding that whether one liked the look of the wind project and the correlation to annoyance there. The question said, is this saying that people who like the look of the project also find it annoying, or am I misinterpreting the image? Yeah, so that's actually an inverse correlation. So those who do not like the look of the project were more likely to find shadow flicker annoying.
Actually, it is also, I believe it takes into account whether you do like the look of the wind turbine as well. So it's taking, allows the respondent to say that they don't like the look of the turbine or they do like the look of the turbine. Yes, it is an inverse relationship, but we're actually asking them both of those, or they are able to answer the question in both of those ways.
Well,
Yeah.
they could also be neutral.
They could also be neutral.
Yeah.
Yeah.
And then just one more that was already answered was a clarification about the statement that 90% of the homes are protected by a 45 decibel setback. So the question was, did the model actually know where the homes were, or is this simply referring to 90% of the surrounding land? And in our modeling, we did actually use XY coordinates for the residences themselves. I don't know whether any of the others would have anything to add there.
Yeah, and this figure isn't descriptive of where those homes are, but yeah, we knew exactly where the turbines were, where the homes were in and around the turbines, and this is just this particular figure is just showing you kind of the overlay of just shadow flicker and sound, not as well the homes that would exist in this area.
Excellent. Well, let me move to a few of the open questions here. Let's start with this one. So it says, it looked like a few people who had no modeled shadow flicker on their property reported perceiving it and being annoyed by it. Is that correct? Ryan Hawk, I don't know, I propose maybe you could answer that.
Yeah, I started typing, but decided it'd be easier to just answer it with a voice. Yeah, so I guess the first thing is that we modeled shadow flicker at residential points. So we're not really making a statement about what the shadow flicker exposure was on their property. So it's certainly very likely that people may have, been annoyed by the shadow flicker on their property as opposed to their home. And so that's why when we look at annoyance, we're really just limiting that to those with shadow flicker in their home. But yeah, there were certainly just a couple, I think on the previous side, it's maybe a little more noticeable that with 0 hours of shadow flicker exposure, they are reporting some form of either perceived shadow flicker or annoyance. It's a very small number, but that could be a number of things.
And we also found this occurrence as well for sound, where one would assume that the turbine was far enough away and the sound levels received at homes were low enough that they were very unlikely to actually be able to hear the sounds of the turbines. Yet they still, some individuals that responded to the survey claimed that they could hear them and they were annoyed by them. So there might be some relation to that occurrence where they marked the survey as such, yet maybe didn't have the basis for doing so.
Okay, excellent. So moving to another question. So Ruchi asks, have you all observed a correlation between this issue being shadow flicker and NIMBY, which for those who may not know stands for not in my backyard? I guess I'd posit a quick response here and invite others as well. But in the past, we've done a lot of research focused on attitudes among those who live in proximity to wind turbines, and developed another robust regression model in this area. Shadow flicker was, or the self-reported perception of shadow flicker was a parameter in that model. And amongst the full model with all the variables we looked at, it ended up not being statistically significant when it came to attitudes among those living near existing wind projects. Now that may or may not be the same thing what the questioner means by NIMBY. But I guess I will say that the NIMBY framework is also something we've kind of tried to avoid, as it tends to be considered pejorative and not necessarily kind of explain opposition, but perhaps maybe be more a response to opposition. So hopefully that adds some clarity. I don't know, do others have anything to add there? And maybe I'll send a link to that paper that did examine that in the chat as well.
Yeah, and I think it's worth noting that this is one of the issues that's brought up regularly by communities that are considering a wind project in their area. They would want to avoid scenarios where they are experiencing shadow flicker on homes. They want to avoid scenarios where they're loud turbine noise is particularly high at homes. These are issues that are brought up regularly in communities as they are considering a wind project in their area.
Excellent. So this was an interesting question. So it's referring to slide 18. Did you correlate the house directional facing to perceived annoyance? So for example, if a house had a lot of shadow flicker exposure, but north facing windows, they might have no perceived annoyance due to structural issues. Or on the other hand, if we have less than 8 hours of shadow flicker, but south facing windows, maybe there would be more annoyance. Ryan or Ken, do you want to touch on that? I mean, basically, we didn't have the data for
or we didn't have the grad students to look into that.
You can drive around and or go around on.
But it's a really good point, and one of the papers that we cited from Johannes Pohl did look into that in more of a case study basis, and certainly found that was one of the missing links, was understanding how the house faces a turbine that's generating shadow flicker there.
Specifically, what rooms are and what the uses of the rooms are, and how often people use those rooms.
Hey guys, so can you talk about some work that we did that didn't end up on, effectively ended up on the cutting room floor? We spent a lot of time trying to find other ways in addition to or instead of just simply the modeled numbers of maximum numbers of hours or cumulative number of hours in a year at the home to predict annoyance. And we're not successful, but we did try a number of things. You guys want to talk a little bit about that? For example, the time of day issue and the frequency, the closest of the turbines that experiences the hours, that kind of thing.
Yeah, I can touch on that, Ryan. You can add to that. You know, so we did look at time of day with some theories that perhaps when people, you know, if the shadow flicker occurred more in the morning when people were just getting up, or whether it occurred during the afternoon when, you know, people who are working away from the home are less likely to be there. We looked at seasonality. We looked at different ways of constructing minutes per day, maximum minutes per day, for example, and other metrics. And for the most part, we got similar results from most all of the metrics. None of them seem to explain better shadow flicker, reaction to shadow flicker.
Okay, great. Let's keep on moving. We do have a fair amount of questions left here. So Ken, the next one for you says, from Chris Olson, our experience is that as you look at taller turbines, so talking about 600 feet or greater, the relationship between noise and shadow flicker doesn't necessarily hold true. So you might have a case where you have greater than 30 hours shadow flicker while still having sound around or less than 45 dB. So thoughts on that?
Yeah, that's true. And I should have caveated the results by saying that that's based on essentially existing technology wind turbines. And as wind turbines get taller and the shadows extend further, and so that while it's still true that there would be a relationship, it may not be true that all of the locations would be less than 30 hours of shadow flicker per year within the 45 decibel contour. Yeah, thanks for that, Chris.
Okay, so next, it says, I'm curious if anyone is looking at that portion of the population that is just generally annoyed, not as people that are fussy or annoyable, but simply because they're more sensitive receivers, sort of like canaries in the coal mine, and might thus be viewed as useful. I think that was written into the survey. So yeah, Ben, it looked like you navigated to this slide. You want to touch on that? The general annoyance?
Yeah, so these are I think those canaries in a coal mine. These are the individuals that generally had higher levels of annoyance to environmental perturbances as it relates to, but potentially as it relates to shadow flicker. So these are sounds that might be experienced in the community, traffic noise, those sorts of things. And sure enough, they were more likely to be annoyed by shadow flicker. And I believe the same is true for noise. We found that individuals who considered themselves, this is self-reporting, that they were more sensitive to noise tended to be more annoyed by the noises of the wind turbine. So those are definitely our canaries there. I don't know what percentage of the population are like that. I guess we could pull that out from our sample because we did take a random sample, but it's a good point. And potentially they're different than the population that tended to maybe be less annoyed by the shadow flicker and less annoyed by the noise of the turbines than their cohorts.
Yeah, great. And I think that answered another question on our list here from Jiang Lin, which is, what is the general annoyance variable? So I think we just touched on that as well. So let me ask a kind of technical modeling question. This would be a good one for Ryan Darlow. For the modeling of shadow flicker, did you use a proxy receptor, for example, a 1 meter by 1 meter square, or did you model actual windows to compare perception inside?
Yeah, great question. The window answer is the same as before, where we didn't have the resources to do that. So instead, we used a 1 meter by 1 meter, what's referred to as greenhouse mode. So it faces all direction window. It's a conservative approach, but it's pretty standard within the industry.
Excellent. Thanks, Ryan. Okay, have you found any correlation or relationship to landowners receiving payments for wind versus non-participants? I don't know, I'd say, Ben, you want to start with that?
Sure. So those individuals that were hosting wind turbines on their property, we found in the attitudinal survey were in general had a slightly higher, a more positive attitude than the others in our sample. The other two groups in the sample were those individuals that were receiving money and not hosting a turbine, and those individuals that were not receiving any money. Their attitudes were not statistically different from each other. So that's as it relates to attitudes. It was not something that we looked at in the shadow flicker paper. I can't remember whether it was looked at all in the noise paper.
No, I mean, we kind of did look at that in using it as a variable in the regression model.
Okay.
So for example, when we looked at a regression model that only used those basic variables, just, you know, distance, project participation, and estimated shadow flicker exposure,
There we go.
project participation was actually the most significant in that case. But once you add the subjective variables, the attitudinal variables, it just kind of blows everything else out of the water. You know, I guess what I'd say about like the basic annoyance model is that its predictive power was really poor. It was, you know, 50% predicted correct out of 3 groups. So, you know, might as well just draw straws. But really, as we once we added the subjective variables, that's where a lot of that predictive power came from.
Yeah, so, and to be clear, to those 2 groups I mentioned, project participation includes both hosts and those individuals that were compensated that don't host a turbine.
Okay, great. Moving on, we've got a couple of questions here related to kind of regulations and appropriate standards or limits for shadow flicker. So the first one says, you know, given that the exposure of shadow flicker is not necessarily correlated with annoyance, is it fair to say that an ordinance with no more than 30 hours of real or actual shadow flicker at non-participating homes is a reasonable standard? And then similarly, would you say that based on the responses you received, you can confirm the 8 hours per year real case is an appropriate guidance limit? So again, we're kind of seeing this confusion between the 8 hours and the 30 hours between real and worst case. And yeah, Ken, I guess I'd pass it to you to give a response here.
Oh, thanks, Joe.
You can pass the buck to someone else.
Yeah. You know, it's interesting that at about 8 hours per year real case, only about 50% of the population even noticed any shadow flicker at their home. But once you observe shadow flicker, then it's about, you know, no matter how much shadow flicker you have, you seem to be just as annoyed by it. So it's a really good question about, you know, at what point then do you set your standard? And at this time, I'm not going to recommend anything, but I think that's just an important thing to point out. Anybody else?
Nobody wants to touch this one.
I'll only add that you needed to have perceived shadow flicker to be annoyed by it. So maybe the goal should be looking at reducing the percent of the population that can perceive it at all. So, maybe there's something to think there. Obviously, the conservative limit of 30 hours a year real case would avoid, 8 hours a year real case would avoid many individuals from even perceiving it.
Yeah, and clearly, so Chris has followed up with another question. Clearly, he wishes he could unmute here, just join us. But so given that there's not a dose-response relationship between exposure and annoyance, he says, doesn't that mean there's no need for any standard, let alone 30 hours? And I mean, again, this is an interesting point. Like, these regulations are designed to reduce annoyance and protect community members, and if they're not doing so, maybe that's problematic, but I don't think we jumped quite that far to that conclusion. Yeah, Ben, Ken.
Yeah, I'll take just to note that, look, the shadow flicker hours, because of sound, as Ken mentioned, are relatively low in a real case basis. They're also often regulated. So maybe what most individuals around wind projects are actually receiving is at a level that doesn't maybe drive them to the point of annoyance that we could measure it. And their annoyance factors related to the project or related to other things more strongly. If we were to just sort of uncap it, that would be maybe a different story.
Yeah, we're getting a lot more chatter about this point. So yeah.
And we do have to be conscious of the time. Sorry to cut you off.
Yeah, we're wrapping up. So I do want to maybe move to one or two other questions if we have time here, and we can circle back with these individuals for a more robust conversation there. So let's answer this one. Was there any examination of how much shadow flicker is experienced in any one instance? For example, 5 minutes of flicker at a time versus 15 minutes or more?
Yeah, Ken, I'll take that. Ken touched on that, and we did look at metrics like that. And I think what we found is it's the kind of thing that is more suited to case studies where we have more information about an individual or that specific home and the time of day. Are they even home when this is occurring? If there's over 30 hours of shadow flicker and people aren't home, who cares? Maybe the dog, but yeah, so there are certainly other ways to look at this, but I think they require significantly more information about each individual.
And I guess I'll try to wrap it up here. I do like the last question, which is, basically, if we are concerned about annoyance from shadow flicker, how can we make turbines look nicer? These are great attitudinal questions. There's lots of strong attitudes around wind projects. We've had a chance to look into the issue of shadow flicker in a little deeper way and hopefully provided everybody on this call with information that they can use. We look forward to more discussion on this. We've provided our emails to do so, so please feel free to reach out to any one of us. And of course, you can search the paper up and you should read it. And hopefully we can continue this discussion. Thanks everybody for attending today. It's been a lot of fun, great questions, and we look forward to seeing you out in the real world.